All right. Is this microphone working well? Okay. Well, yeah? All right. Well, thanks a lot for the invitation, Piotr. And I'm sorry for not having attended any of the other talks here because I only planned to come to the seminar here, but it's still very nice to be able to speak in front of you. The work I'm going to talk about is joined with Hamid Massoud from Imperial College London and Istvan Kadar. It's all part of a series of papers called The Case Against Smooth on Infinity and some number. So I'm mainly going to talk about 4 and 5, which have appeared at the beginning of this year, and upcoming work, which is about to appear soon. And since this is a relatively a bit of a broader audience, I'll try to not be too technical about anything and rather give more of a historical and physical embedding into all the stuff that I'm doing. All right, so what I will do in this talk, let me tell that to you right away. I will physically motivate and explicitly construct mathematical solutions to the linearized Einstein vacuum equations around Schwarzschild, which have the following 5 features. Firstly, they describe the far-field region of a system of n infalling masses coming from the infinite past and following approximately hyperbolic Keplerian orbits. I can also consider other things, but this is the main thing to keep in mind. Secondly, they have no incoming radiation from past non-infinity. Thirdly, they violate peeling near past non-infinity. So near scry minus, the extremal component of the Weil tensor C4 decays like r to the minus 4 rather than r to the minus 5. And fourthly, they violate peeling near future non-infinity as well. So near scry plus, this other extremal component of the Weil tensor C naught decays like r to the minus 4 plus r to the minus 5 log squared r rather than r to the minus 5. I'm lucky to still have peeling written down here, so r to the minus 5 with peeling. So in particular, the constructed class of spacetimes has a direct physical motivation and does violate peeling everywhere. And fifthly, these spacetimes decay slower towards spacelike infinity than typically assumed in most stability works. So this 5th point is more of interest towards people who work on stability problems in mathematical general relativity, but I thought I might still want to point it out here. Right, so that's the general gist. In principle, you could go home now, but now I will give a bit more detail. So I'll first talk a little bit, give a more broader introduction to the general problem of kind of guessing asymptotics in relativity. Then I will talk, this part will be quite physical. I will talk about the generation problem of gravitational radiation. The third part will be more mathematical. I will talk about how gravitational radiation will propagate through vacuum. And finally, I'll conclude with some further comments on that all. So let me start properly. So in general, whenever we have any physical system, we typically want to set some mathematical model up so that we can start studying processes in isolation. In Newtonian theory, for instance, this is conceptually extremely simple. If you want to, for instance, describe how Earth and Sun move around each other, you just replace everything else by vacuum, disregard any interaction that is non-gravitational that you want, and there you go. That's a model of an isolated system. In relativity, this is no longer that easy because even in vacuum, the Einstein vacuum equations are still a highly complicated system of PDE, and there is gravitational radiation floating around everywhere. So it becomes more difficult. And very informally speaking, describing an astrophysical process in isolation, trying to do that loosely corresponds to demanding that the gravitational radiation associated to this process should suitably disperse at large distances. This idea is captured by various notions of asymptotic flatness in the literature, and I will cover some of these notions now. But this is kind of the conceptual issue at the heart of this all. So probably the first and most important work on asymptotic flatness was this work initiated by Bondi, Sachs, and collaborators in the series of papers Gravitational Waves in General Relativity. And I think it's hard to overestimate just how big of a role this played in informing the current trends in theoretical physics. So one of the crucial questions they implicitly ask is, to what extent can we understand aspects of spacetimes by just analyzing their asymptotic properties without specifically understanding what's going on in the interior of the spacetime? So the first thing the authors did was pretty much to understand conditions that guarantee that a given asymptotic region of spacetime would have no incoming radiation, where incoming radiation means any radiation that comes from past null infinity. And motivated by linearized gravity around Minkowski, they argued that if there is no incoming radiation, then the gravitational field should admit 1 over r expansions towards future infinity for some suitable variable 1 over r. Mathematically, this is already a very interesting statement, and even in Minkowski, it's not proved. No one knows if it's true. But it's interesting, and it was whatever they argued was good enough for people to just roll with it. Operating under this assumption, they then furthermore constructed these Bondi coordinates with the 1 over r expansions that Mark just wrote down. And in particular, they argued that the Weyl curvature tensor appeals towards scribe plus, where these psi are exactly the same thing that Mark introduced. So these 5 things. Right, so, and like many important predictions came out of this whole framework, such as the Bondi mass loss formula, the BMS group, and many other things. But of course, how valid all these assumptions are, this was never quite clear, and there were early works that tried to weaken these assumptions by, instead of considering 1 over r expansions, considering polyhomogeneous expansions. Okay, but this was kind of the first big model, yes? I'll get back to that. Look, first, this is just a proposal for now, how to model isolated systems. So extremely shortly after that proposal, Penrose published a paper in 1963, which captured this idea with a much more geometric flavor. So that is Penrose's famous smooth conformal compactification, the idea that you embed your physical manifold into some larger manifold with boundary, such that you conformally embed that such that the conformal manifold extends smoothly all the way to the boundary. And this property of you being able to conformally extend all the way to the null infinities implies this peeling property that I also wrote on the previous slide. So if you have a smooth future null infinity, then it is implied that you have peeling towards future null infinity. Similarly, if you have a smooth past null infinity, then it is implied that you have peeling towards past null infinity. So peeling towards past null infinity is the same thing here, just with the order. So you would start with 4 here, and then 3, 2, 1, 0. It's just swapped around because the L and N switch roles when you reverse time. I should already say this, the peeling towards the future null infinity, that was heuristically motivated by no incoming radiation. Peeling towards past null infinity never had any motivation. That would just be a consequence of having a smooth past null infinity. Okay, so this was Penrose's asymptotic simplicity, smooth null infinity. And of course, for both of these proposals, the conceptual approach is that you that you kind of posit what the asymptotics of some spacetime should look like without directly taking into account what kind of physics might be described by that. And there is basically one exception of physical systems for which there is a clear connection of these models to physics. So it turns out that if you have a spacetime which was exactly stationary up until some finite retarded time, and then somehow something breaks the stationarity, then in such spacetimes you do have a smooth null infinity, and you do have 1 over r expansions. So this is exactly this paper by Blanchet that you're referring to. Blanchet assumes that up until some finite retarded time, the spacetime is exactly stationary. Okay, but that's of course an extremely strong assumption, and you want to understand what happens when you weaken that to only decaying towards the infinite past. In particular, it's not directly, it's like assuming that something goes from non-stationary to stationary is anyways, and I'm sure Piotr will talk about these kinds of results a little bit more. So basically, the only thing that we know is if the data are trivial around spacelike infinity, then here we'll have a smooth null infinity, and once you have a smooth null infinity somewhere, this thing will propagate. Okay, but these were a few examples. Now, of course, relativity is not a theory where you make global assumptions. It's a dynamical theory, and solutions in GR arise from initial data, according to this most important theorem of relativity. So in a suitable gauge, the Einstein equations become hyperbolic, and you can pose initial data, which consist of a Riemannian manifold together with some symmetric 2 tensor K. You also need to specify some constraints. And then this famous theorem says that if these data are suitably regular and solve these constraint equations, then there exists a unique future development of these data that restrict to the data. Okay, so this is now kind of already quite in a very different spirit, because the previous two concepts, they always made global assumptions on the behavior of spacetimes. Now it turns out that even in this dynamical context, you can show that the global assumptions made on the previous slides, they are dynamically consistent. That is to say, if you assume them on one outgoing cone, then they will persist to the future, though that was also only shown much later. But okay, even if we take this mathematical approach of just working with initial data, we run into the same problem. So in 1993, this is considered by some, well, there was this very monumental work by Carrollian and Kleinemann, which showed that if you take the Minkowski initial data, perturb them a little bit, then solutions ultimately converge back to the Minkowski spacetime with quantitative rates. This was a 500-page book. But again, Carrollian and Kleinemann had to make certain assumptions on what class the perturbations of initial data should lie in. So in particular, what they assumed is that the metric perturbation would have a Schwarzschild part plus a part that decays like r to the minus 3/2 minus epsilon. And just as all the previous proposals, this is a concrete proposal to say that well, they make some assumption on initial data, and basically their proposal would then be, if you interpret it physically, that isolated systems should be such that the initial data they induce have this decay. Anyways, 1 power faster. Wait, you mean k, or you mean 1 power, so r to the minus 5/2 minus epsilon. I don't know what the symplectic potential is. This is outside of the language that I'm familiar with. Maybe someone else knows. But anyways, with all these initial data problems, the point I want to make is whatever initial data problem you study, you always need to make some assumptions on the asymptotics of the initial data, and that is at the end of the day just another ad hoc assumption on what the asymptotics should be, but we don't have direct physical access on that. Should also just, as a loose aside, Carrollian and Kleinemann found curvature decay rates which were strictly weaker than peeling, but again, there is no specific significance to that statement because they just worked with another model that had different predictions. Okay, so these were a couple of proposals for how to model isolated systems. Now let me put this, to maybe round this whole picture up into a more global picture where these questions would come up naturally. So for instance, let's say we have some gravitational wave, we have some spacetime which gravitationally collapses to a black hole or something, and we have a gravitational wave detector sitting at null infinity, and we try to measure the radiation at late times. And of course, the way to like if we want a mathematical prediction what that decay at late times is, what we do is we can consider an initial data problem like this, and then we will find that the decay at late times will in fact be dependent on whatever you assume the initial data to decay like towards future null infinity. Okay, and then you can ask yourself, well, what should this decay towards future null infinity be? You could impose peeling as posited by Penrose. You could impose a smooth infinity, but okay, in general, like in order to properly go away from this guessing game, the right way to talk about it is to go all the way back to the infinite past. So you can ask, how is the asymptotic structure of gravitational radiation here related to the gravitational radiation emitted at very, very early times by the system under consideration that you're studying? And then finally, of course, you need to understand what the structure of gravitational radiation emitted by whatever system you're studying is. But this is basically the global framework, which I just gave an example here to hopefully justify to you why one needs to understand all of these questions a little bit to make proper models in relativity. Okay, so that was a bit of a general historical overview. Now, what I want to propose in this talk is that we take an approach towards modeling isolated systems that is exactly based on understanding the infinite past behavior. So it'll be a two-step approach. Firstly, so the concrete plan for this talk, though it works more generally, is to study the generation problem of gravitational radiation for the two-body problem up to some finite advanced time using perturbative methods. And then once we reached that finite advanced time, we want to rigorously study the propagation problem of how gravitational radiation propagates towards future infinity from that finite advanced time. So these sentences are maybe a little harder to understand, so I drew some pictures which have their analogs on this blackboard here, so that you can refer to them whenever you want. So basically, what we want to do is we want to consider, let's say, two infalling masses which come in from the infinite past, and then we want to apply some heuristic perturbative framework to understand how these masses will radiate up until some finite time. So the idea is that these masses will inevitably have to move away from each other, and Newtonian theory becomes a better and better candidate, so that the prediction we get from post-Newtonian methods becomes somewhat trustworthy. That's the idea. But this is a completely heuristic part of the talk, where I won't prove anything. I will just justify certain things. The point is that we ultimately want to get a prediction on what the gravitational radiation will behave like on this null cone. I chose a random null cone that encloses the system. And once I know this, I then go to the mathematical part of the talk, where I just post data on this null cone as predicted by the previous part of the talk, and solve to the future just by mathematically analyzing the Einstein equations. And no. So this is passed on infinity here. This is the null cone. Let me. So this thing just patches into here. I go from here to here. Importantly, in the heuristic part of the talk, I will talk about linearized gravity around Minkowski, and in the second part of the talk, I will talk about linearized gravity around Schwarzschild, because as it turns out, in order to see the failure of peeling, you need to go to higher order in perturbation theory, and the cleanest way to do it is to perturb around Schwarzschild directly. Anyways, that's the, yeah? But the point is that everything here only takes place near the far infinite past. So this is way before black hole formation. Yeah. 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 So again, the unreflected assumption that I'm making here is that asymptotically flat spacetimes are a good model to work with to begin with. Could also consider cosmological constants, and then who knows what will happen. But it's maybe a step in reflection higher than the previous ones, but it's still nowhere near a proper satisfactory. Yeah, this cosmological constant problem is a whole nother beast. Okay. But so this is the general idea. I will explain each of these parts separately in separate parts of the talk. Yeah. Yeah. I think maybe ask the question again once I explain the framework, or maybe I'll just remember your question. But I think it's best if I talk about it once I'm there. But this is a yeah. Well, let me stick to what I said. Yeah. No. No, it's really n masses. And okay, whether these masses Okay, I'll talk about it in a second. These two masses are just one example, and I'll give you a few other ones which are relevant, I think. Right, so now I'll talk about this generation problem with a slightly higher degree of specificity. Okay, this will all take place in Minkowski spacetime, so I'll very briefly introduce that. So Minkowski spacetime is this thing, and well, we can introduce these double null coordinates. I will always be working in these double null coordinates u and v, which I drew down here, just so you can always refer to them. And okay, of course, in these coordinates, the metric takes this form, and you can conformally, like, you can just map these double null coordinates to a set of bounded double null coordinates, which produces this Penrose diagram, where future infinity just corresponds to the limit points v equals infinity, and similarly for path on infinity. And okay, you can take this picture on the right much more seriously and actually view these boundaries as part of the spacetime by doing a conformal transformation, but this is what ultimately led to Penrose's smooth on infinity, but this is not what these pictures require. They're really just mapping a set of unbounded coordinates to a set of bounded coordinates. Okay, this is Minkowski, very good. Now, linearized gravity around Minkowski, I won't say all that much about it, but if you linearize the Einstein-Vacuum equations around Minkowski and impose wave gauge, then the general outgoing solution for the metric perturbations, at least on fixed spherical harmonics, is, well, you can write it like this is just like proof of concept. It exists somewhere here. This is from Kip Thorne's review paper from 1980. Okay. And now what we want to do is, well, we know that this is the general form. In this talk, I will mostly talk about these Newman-Penrose scalars, psi0 and psi4. So I'll spend a little bit of time I will basically compute psi0 and psi4 starting from this expression. And okay, I'm lucky that Mark already defined these for me, but I am using exactly the same definitions. So basically, a lengthy computation gives you this expression for the two Newman-Penrose scalars, psi0 and psi4. Where L and M denote the indices of spherical harmonics, tensorial spherical harmonics. Now I find this a bit hard to read, so let me just write it down for L equals 2. So for L equals 2, this is the lowest angular mode for psi0 and psi4. We will have some function of u over r to the 5, and for psi4, we will have 4 u derivatives of some function of u over r. Okay, and the general expression just has more derivatives in between these things, but it's essentially similar. And it's noteworthy here to note that these expressions are such that we always, no matter what these functions of u do, we always have a 1 over r expansion towards future infinity. And we always have these peeling rates here. So in Minkowski, this was the historical motivation for why people thought that peeling was a real thing. Okay. So this is how you compute, you compute psi0 and psi4. Next step is, okay, psi0 and psi4 depend on these general functions of u. And now I do some matching to post-Newtonian theory to compute those. So if we make the usual post-Newtonian theory expansions, you derive that these ILM and the SLM are basically the Newtonian mass and current multiple moments. This is all still contained in Thorne's 1980 paper. So this is exactly the usual. Rho is the mass density multiplied by r to the L. This is exactly the Newtonian mass multiple. Okay, so now finally we need to consider a very concrete physical system, and we consider that of n infalling masses. Now when we consider n infalling masses in a theory where there is a radiation, then for the same reason where the hydrogen atom is classically unstable, we are bound to consider unbound orbits in the infinite past, because any bound orbit would conspire to decay in finite past, right? So we either have to consider essentially parabolic or hyperbolic Kepler orbits near the infinite past. At the same time, it's nice because we know that if these things move far away from each other, then Newtonian theory is a very trustworthy friend. Okay, and then now I'm just citing some things from basic celestial mechanics. So for hyperbolic Keplerian orbits, you may recall that the leading order behavior of the relative position vector between any two particles goes linearly in t, so v times t, and then there is, at next leading order, there is a log t term, which just immediately follows from Newton's law. So in particular, the Lth multiple moment will go like t to the L plus t to the L minus 1 log t. So now finally we bring all these things together. So recall perhaps for psi naught, I said this is like I of u over r to the 5. So and I of u at L equals 2, this will go like t squared. And t is like u is like r near past infinity. Long story short is that psi naught will go like 1 over r cubed. The next term will come from this logarithmic term and will be log r over r to the 4. Then there will be 1 over r to the 4 term. And you get a very similar thing for psi4. Now, for L equals 2, these results have also been known for a long time in the physics literature. Walker and Will proved this, well, they argued for this in 1973, I think. And you may notice already that the decay rate for psi4 violates peeling near the infinite past. But that's not really something that's super concerning because no one ever argued for peeling in the past anyways. So that is basically the generation problem. So we basically, what we take away from this is, that psi naught decays like r to the minus 3 here, and psi4 decays like r to the minus 4 here. Okay. Are there any questions on this generation problem part of the talk? Right, yeah, things are, so yeah, if the transformation scribe minus to scribe plus is 4 goes to 4 minus, so I goes to 4 minus I. Yeah? Well, at this order, no. This is just, this directly is done in the Donovich. At this order in perturbation theory, as long as you choose harmonic gauge and work in a center of mass and so on, then this is just what you get. Be sure. But anyways, you know this probably better than me. But either way, these quantities, the reason why I talk so much about these quantities is that they are gauge invariant. What? Yeah, at the very end of the talk, I have a slide which does the same thing in the future in Bondi coordinates. But, huh? Yeah, but it's the same thing in the end. But I think it's, so you have, the G has a 1 term and a 1 over R term and then a log over R squared term. But I'll show, maybe at the end of the talk, this will become a bit clearer. But anyway, like G itself is not, the reason why I like talking about these things is that they are independent of the, of course they depend on the frame, but they are not dependent on the gauge choices. Yeah. But the thing is that there are also gauges in which G always behaves a little bit badly towards past and infinity. It's just not a natural object to study in certain contexts, and I think of, in the harmonic gauge,
You're talking about the Lorentz gauge. In the Weiss scalar, you're saying the
well, if you want to change your frame to if you want to weight your frame with R weights, then you make null infinity into a very strange object. So then the spheres at null infinity are no longer defined, and like at leading order, they just all blow up if you change the frame. Because in order to change this, you need to. Yeah. Now it's no longer full screen.
Something done first by
Yes, Damour did Damour did the second part, provided an, I'll get to that, the second part. This first computation, like I said, this is just a mild generalization of Walker and Will, and it's really just serves for motivation for what data I choose. So maybe final aside here, it's noteworthy that all angular modes decay with exactly the same rate. Like typically in multiple expansions, you expect that higher multiples decay faster. This is not the case here, simply because the system itself grows linearly. And this makes this problem actually mathematically quite difficult. Okay, but this is all I want to say about the generation problem. There is one, because maybe it's not super satisfying for me to rely on heuristic results. So there is an alternative way I can essentially produce the same rates. And that is if I simply consider linearized gravity around Schwarzschild or Minkowski, and I say that I have some compactly supported bump of gravitational radiation living at path and infinity, and I just wonder what this will radiate like. So think of this as a few gravitons coming in from path and infinity. And so essentially this gives the same rates morally. There are some differences, but morally they are not relevant. The point here that I want to make is that if you don't like this heuristic part, you can replace this whole picture of n infalling masses by n infalling gravitational perturbations, and then it's rigorous. But that's, okay, I'm not explaining that now. But. So now I want to, so I've talked about this generation problem now, and now I want to, so now I know what psi at naught and psi4 decay like on these null cones, and now I basically use that as an initial data assumption here, together with assuming no incoming radiation here, to just solve what will happen towards future null infinity. And maybe I can already say it now. So Damour already did in principle a very similar thing, just only for L equals 2, and it wasn't quite a proof. But essentially Damour in this way found that future null infinity would not be smooth. And then there was another heuristic argument by Christodoulou, which also gave predictions that under this setup, future null infinity would not be smooth. And the place of my work is to make these arguments, to round them up and paint a complete picture for that. So the propagation problem. So this is now taking place in Schwarzschild because, as I've just shown you, in Minkowski, you will never violate peeling if there is no incoming radiation. So either you go to second order in Minkowski or you go to linearized gravity around Schwarzschild. So maybe first, let me just introduce linearized gravity around Schwarzschild. So first, okay, we again introduce these usual double null coordinates so that G, the Schwarzschild metric, takes this form. Here's the Penrose diagram, but I'm sure you're all familiar with that. And okay, we only work in this quadrant of the Penrose diagram, away from the event horizons. We just want to capture the fact that there is mass near space like infinity. Okay. So what we'll do is we'll linearize the Einstein vacuum equations around the exterior of Schwarzschild, but in a double null gauge, not in harmonic gauge. So that is to say, we write down a one-parameter family of solutions to the Einstein equations in this form, and then we linearize in epsilon, and we get a bunch of resulting equations. So there is a bit of a jump scare now. These are the equations. So this is the set of unknowns, and these are the equations of linearized gravity. These are the Bianchi equations. And okay, one thing I want to say is that the concrete motivation for studying linearized gravity around Schwarzschild is not just to capture some effects that are not present in Minkowski, but because it turns out that this is exactly what you need to understand as a precursor to treat the actual Einstein vacuum equations, which is ongoing work to basically do this entire part of the talk, but with the Einstein vacuum equations, with no reference to any background. And it just turns out that understanding linear stability on Schwarzschild is linear, at the linear level, that's all you need to understand. Okay, so this system, this relatively complicated system of equations was first properly unlocked in the seminal stability result of the famous Hodgsky-Rudniansky, and I'll just briefly go through some key observations for those who care, but it doesn't play a huge role in this talk. So firstly, in this double null gauge, they separate out two explicit classes of solutions to the system, namely the solutions that arise when you linearize a neighboring Kerr, and the solutions that arise when you linearize a gauge transformation that keeps the double null gauge intact. So you need to understand these solutions explicitly because they carry the unphysical degrees of freedom in the problem, and sometimes you need to get rid of them to understand certain things better. Helpful in this not having to worry about the unphysical parts is once again the fact that the Newman-Penrose scalars psi0 and psi4 are gauge invariant. And so they are unaffected by these unphysical solutions. And not only are they gauge invariant, but they satisfy decoupled wave equations, so-called Tchaikovsky equations. And this is very nice because this means that we don't have to study this entire system all at once, but we can just look at two quantities which satisfy decoupled equations, the Tchaikovsky equations. And now the Tchaikovsky equations themselves are actually still a bit hard to deal with from a mathematical perspective. That's because they have first-order terms. But these first-order, like they have first-order terms with certain bad weights. But these first-order terms, they can be removed by basically suitable commutations with some vector fields. And at the end of the day, you can make out of these psi0 and psi4 some quantities that just satisfy the Reggie-Wheeler equation, which is the usual wave equation, the tensorial wave equation, essentially. And then you can treat that by standard methods. Once you control that, it turns out that together with the control of the Reggie-Wheeler equation and a lot more work, in particular, being very careful about all the unphysical degrees of freedom here, you can control the entire system in the end. This is a brief summary of what their proof achieves. Just to give you some context for how the system is dealt with, because I think it's not super, may not be super familiar to everyone. Okay, so what we want to study is, of course, this problem. So I want to pose certain data on this null cone, and I want to pose certain data in the infinite past. So this is not a usual initial value problem, but this is more like, given these asymptotic initial data, I need to find a solution that approaches these asymptotic data in the limit. This is slightly different. So the first thing to figure out in this problem is to understand what the data consist of. And okay, I'll only read the red and bold font things here. So along this ingoing null cone, you need to prescribe the ingoing null shear. Along path and infinity, you need to prescribe the outgoing null shear, which is the same thing as the News tensor. And finally, this is slightly funny, on one sphere up here, you need to prescribe the transversal derivative of psi4. You also need to prescribe all kinds of other quantities, but the nice thing is that all these other quantities, which I didn't mention now, they can be just set to 0 by addition of these pure gauge solutions. So they don't carry any physical degrees of freedom, in other words. And this is basically, in spirit, very similar to Bond denormalization. So for instance, part of the data would be to specify the Gaussian curvature here, but it turns out that you can always set the linearized Gaussian curvature to 0. Makes the spheres round, things like that. Okay, and then I won't talk much about it, but so basically, given such initial data with a certain degree of regularity, then there exists a unique solution in the entire domain of dependence, so in this entire Penrose diagram that restricts correctly to these data. S1 is this sphere up here. So on one sphere along the cone, it doesn't matter, I just picked a random one. You need to specify some extra information on one of these spheres. That's a very good question. Thank you for. So I'm cutting this entire problem off at sufficiently early retarded time. So so let's say this is u equals -1 seconds, and this is u equals -1. Because the point is that in order to understand what happens near future null infinity, I only need to get beyond spacelike infinity. And this is, for reasons that I will explain later, this is all we care about, just to get some piece of future null infinity, because that will tell us how smooth it is, and it turns out that that will be, in some sense, conserved for all times. Well, okay, so there are two ways. There are two ways you can think of this picture. Either you say we look at the entire Schwarzschild metric, with this being the past event horizon, and then you have compactly supported data here, and you can either now say, well, I say that the solution is exactly 0 here. I have a trivial solution here. This gives me trivial data here. So here, then this, sorry, this is probably too small. This dv C4 would just be 0 because it's trivial. And then here now I can just solve forwards, where these are now part of, this is just encoded in the null outgoing null shear along null infinity. So this is one way of viewing that. The other way of viewing that is to just, no, actually, yeah. So this is one answer that I can give. The other thing is you do the same thing, and then you only evolve up until some cone here. And then, of course, you can compute how this bump will have affected everything on this cone in particular. It will tell you what dvpc4 is. But the point is dvpc4 never plays a role. You just need to specify something, because it's just a finite value of some quantity. It won't affect it. Asymptotics, if anything. Well, I mean, okay, on the one hand, so each of these is a symmetric trace-free 2 tensor, so this adds up to 6, which is what you might expect in 4 dimensions. On the other hand, why exactly these quantities can be gauged away, and apart from the fact that you expect to be able to reduce to 6 components. So the way it works exactly is that you have, I can write down basically the span of all gauge solutions explicitly. And so basically the gauge solutions either come from transformations in V, or from transformations in U, or from transformations in the angles. And so I've got a set of linear independent gauge solutions, and I can hand by hand subtract, like give me any initial data, and I subtract one after the other to, in a suitable order, kill off all these terms. But I mean, that is a very technical answer, which is probably not illuminating. But like setting all these to 0, so all these other things, I always try to include the word, because we probably use different notation. This is the fact that you can normalize the Gauss curvature to vanish at the linearized level, which means that the real thing is the background thing. This is what you also do in the construction of Bondi coordinates. Then the fact that the weighted outgoing null expansion along path on infinity vanishes. This is just to say that the spheres along null infinity, they don't grow in any way, but they may twist. And similarly, you can make this cone such that the ingoing null expansion is to leading order 0. And so omega omega is this thing. So this really means that you can, to leading order, make the metric look exactly Schwarzschildian. Except for the shears and this ominous thing. Okay, so this is basically the existence theorem. And now we know what kind of data we need to pose. And now we want to pose data such that they agree exactly with the previous prediction from the generation problem. So I want to pose these data that psi0 decays like r to the minus 3 and that psi4 decays like r to the minus 4, which is what I'm doing here. So I'm giving you this definition that a seed scattering data set is said to describe the exterior of a system of n infalling masses following approximately hyperbolic orbits if the following conditions are satisfied for all angular modes. So psi4 wanted to decay like r to the minus 4. Psi0 wanted to decay like 1 over r cubed. I want there to be no incoming radiation from scry minus, which means that this News tensor vanishes. And okay, I also wrote this condition. This is something that I skipped in the discussion of the generation problem, but basically the ingoing shear has the 1 over r squared behavior there. Again, that's not something hugely influential for anything, so I thought it's okay to skip it. But okay, this is basically, up until now, I've only set up my problem. So that I can now say that solutions arising from these data are suitable for describing the far field region of a system of n infalling masses. Are there questions on just this setup? Yeah? Yeah. So let me be extremely transparent that I'm not saying that any of this heuristic motivation is rigorous. So there is no rigorous matching between these two pictures. I just want to make that clear first before I continue talking. So of course, here, this is a null cone in Minkowski spacetime. This is a null cone in Schwarzschild spacetime. They diverge from each other logarithmically. You could naively say, all right, this certainly won't affect the leading order behavior of 1 over r cubed here, but it will probably give you another log term here, right? Because so it's basically, you integrate one, you have this leading order, they are both the same, but then there is the logarithmic divergence next to leading order. You expect certain things like that. But since there is a log term anyways here, I think that's okay. But yeah, it's really like, there is absolutely no way that I'm telling you, here are results for linearized gravity around Minkowski. They just mathematically apply for linearized gravity around Schwarzschild. I'm not saying that. I'm just saying that from a physical point of view, you would expect them to be the same. But the right thing, of course, is to either do this thing down here, where you replace the assumption of n infalling masses with incoming gravitational radiation, or to treat this generation problem mathematically for the Einstein equations. Because then you don't, because it's just linearizing around two different geometric backgrounds, the objects that arise are hard to compare. And this is an open problem in our field that people work on. So, but yeah, I'm not claiming that you can just smoothly patch these two pictures. Yeah, so so I think to leading order, what you could probably make some heuristic argument that this coefficient is unchanged, and that here there is a M correction from the Schwarzschild metric. But yeah, I'm not making any claims now that these coefficients are exactly those multiple moments. I think it would be very interesting to kind of treat the whole generation problem as a problem for linearized gravity around Schwarzschild, but as you know, there is no, people don't really know how to treat that. Well, that's a good point. Yeah, screw that. That's a good point. Yeah, so no, I think I don't know what I mean, but this is not my yeah, you're right. It doesn't make sense to directly treat the generation problem on Schwarzschild, I think. But repeat the line. Hmm? Okay. Okay, so the one thing that you can always think of is to instead just consider compactly supported gravitational perturbation. And yeah, doesn't make a difference. Schwarzschild-Minkowski. That's one thing you can do. Then you don't have any of this confusion. The other thing is that okay? It gives me this picture as well. Yeah. I mean, okay, you get a 5 here, but it turns out that this change is inconsequential. So this is the one thing that is rigorous that you can do. And then the other thing, but you look like you have another question on that potentially. Well, like I said, this is the thing that's already mathematically proved. Incoming massless objects. Yeah. This thing here, I'm really just giving a heuristic motivation that you basically expect. You expect, for instance, if you do this generation problem just to higher orders in the Newtonian parameters, then the effects of that will only give you subleading changes here, but they won't change the rates here. And then I think it's reasonable to expect that, well, it's just reasonable to believe these rates towards path on infinity. Of course, yeah. Yeah, well, no, they in the infinite past they will radiate 4 times.
Maybe at some point you run into a problem of infrared divergence. That you have particles in an infinite number of. At some point you have an instability problem. Are you going to discuss that? At some point you can show that the second order perturbation becomes bigger than the first order. Yeah. Or you can no longer trust linear approximation. Especially if you violate peeling, you have growth of here you're in approximation where you lose linear theory, but you're in a context where you have infrared divergence because you assume that you emit radiation for So that would generate itself limitation on the problem that you cannot trust anymore your linear perturbation. The quadratic order perturbation will get bigger than the linear one, and then you have to stop doing linear.
By late times, you now mean very early times.
Well, early or late, like it's just if you have this long-term occurring, that's at some point the linear perturbation is no longer, you have infrared divergence. The linear perturbation is no longer valid.
You're saying that you do not believe that psi0 and psi4 decay like r to the -3 and r to the -4 towards path on infinity.
Well, no, it's just that at some point, if you look at the Einstein equation in the book, if you look at Blanchet equation, that there's growing term, the second order perturbation becomes bigger than the first one. So you can no longer trust the equations that you're using in the beginning, which are the linear perturbation.
Yeah.
Because the linear perturbation assumes that first order perturbation has to be smaller than the quadratic. Yeah. So then you have to stop, right? So it's the problem of infrared divergences. You can only trust that if you have an infrared. The order of limit is very subtle.
Okay.
So that's something you have to.
Think, at least here, if I understand you have particles of
Well, they certainly radiate at all times.
They radiate all the time.
yeah, but how much? I mean,
Infinite amount of
Well, I don't know what you mean by infinite amount of
well,
gravity.
you can compute the number of gravitons.
Yeah, that's just a finite thing. I mean, this is really just, I take Newtonian orbits and put them into some background, see what the gravitational field is like.
The momentum aspect. So, yeah, there's something infinite. Sure.
Maybe these data are completely relevant. We have a better presumption about it. Okay, so maybe there's a clear problem, and we see what happens.
Can we ask, there's a question, to what extent can we trust the linear approximation? At some point,
that's linearized theory anyway.
Yeah. So you're in the linear theory, and at some point you have to predict when is you cannot trust the approximation.
Yeah.
No.
But let me be extremely transparent to you. Let me be extremely. So I presented to you an argument that has no mathematical value, zero truth value, but it motivates my data choice. Now, I would think it's one of the most interesting problems in GR to generate truth value from this mathematical problem, but that's not the topic of my talk. But of course, if you tell me that it's likely that these rates might be violated, that makes this problem even more interesting. This is all just a motivating thing. For me, it's very fortunate that you can also always just draw this picture and then everything becomes rigorous. I'm not aware. But I think it would be a nice problem because it seems like in principle, a very simple problem because things go very far away from each other. The difficulties associated to that, of course, are separate from the usual difficulties in that problem. But I think it would be a nice problem to study even from this post-Newtonian perspective. Okay, so let me just state my main result now. So I motivated my initial data, and of course there is a high degree of doubt it's not mathematically justified, but there is some physical argument, and it's not so clear how solid that is. But given such a data set, then we can basically compute the semi-global asymptotic expansions of fixed angular modes of psi0. In particular, there is this 1 over r to the 4 term for each angular mode, then there is a log squared r over r to the 5 term, and there are further terms which I didn't bother writing down anymore. We furthermore have that these limits, to make this slightly easier to read, I wrote this down for L equals 2 as well. So then we have a u squared over r to the 5 term, which dominates near path on infinity, and then a 1 over r to the 4 term towards future infinity. And this 1 over r to the 4 term has also been predicted by Damour and Christodoulou. Now, furthermore, this 1 over r to the 4 term is actually a constant of motion. So along future infinity, this limit is conserved. It's identical to the limit of 4 derivatives of r psi 4. Sorry for the switching around. I messed something up in my code. And finally, I can also compute what r psi 4 will behave like along functional infinity. So, which in particular means that I can tell you how what the News function will behave like along functional infinity as u tends to minus infinity. Okay, So this is basically the result. Now this theorem is just a very specific theorem. More generally, whatever data you give me, I can tell you the asymptotics. But these are asymptotics for fixed angular modes. And of course, then you should also complain, who cares about results for fixed angular modes? There is no way we know how to sum these to the entire solution. And this is the next theorem, summing the results for fixed angular modes. So it's basically not really tractable to try to directly sum these estimates. And instead, the way we approach that is by a soft statement. So we prove that for a general large class of wave equations, you have the property that if you have initial data that have a general expansion in powers of r to the minus p times log n of r, if these data have such an expansion, then the solution will also have such an expansion. This theorem is a very general statement that you can prove. It doesn't tell you, however, what the coefficients in these expansions are. It just tells you there is such an expansion. Yeah? So this is valid for data. You can have also data here, which are polyhomogeneous. This is the statement expansion here, expansion here. But it doesn't tell you what this expansion, what the terms in the expansion are. But the nice thing is, if we already know that there is such an expansion, then we can simply, as a corollary, project back to L modes to understand all the coefficients in the expansion. This is kind of the mathematical approach to summing the L modes softly. Okay, but I guess this is maybe not that interesting. But this is more of a mathematical difficulty. Okay, I would probably have to look up what exactly that is. Well, I mean, up until the 90s, I don't think there existed a scattering theory for wave equations in any form. So it would surprise me if. Okay, but that sounds like a formal argument.
Unless you assume something.
But I mean, in general, yeah, there are many, like, I think your paper is the first argument that tests the formal consistency with these expansions. Yeah. But yeah, yeah. So, okay, I think I've essentially run out of time.
Is it still linear or are you non-linear?
This holds for a large class of linear and nonlinear wave equations, but it in particular applies to this problem. So this result, in the context of this talk, applies to linearized gravity around Schwarzschild. But the general methods you can also apply to nonlinear problems. But for linearized gravity around Schwarzschild, there are many things that are missing. So I've run a bit over time now. Can I get maybe five more minutes, or should I just? Okay, so I'll very briefly just give you a glimpse of the proof because the actual numerology is very easy to understand. So it turns out that Psi0 essentially satisfies an equation of this form. I've dropped a few terms here, but essentially this is the equation that you have. And okay, the crucial observation with this equation is that on the right hand you have r to the minus 7, here you have r to the minus 4 and two derivatives. So you can basically perturbatively treat this right hand side, always integrate twice to improve the power by 1. I'll show you what I mean by that. So we start by plugging in that Psi0 decays like 1 over r, which you can obtain via general methods. And then we just insert this into the right-hand side. So the right-hand side will now decay like 1 over r cubed. And we integrate in u from path and infinity, where by the no-incoming radiation, we won't pick up a boundary term. So this integral will give 1 over r squared. We multiply by r to the 4. and integrate once more in V to get that the difference of r to the 5 psi naught here and r to the 5 psi naught along data is bounded by r cubed. And now you can see this is already an improvement over this 1 over r decay here, because if I divide by 1 over r to the 5, I get that psi naught is bounded by 1 over r squared. So I can keep iterating this to improve the rate to arbitrary precision. So I just changed all the numbers by 1 here and again. So in particular, you find in the end that r to the 5 psi naught to leading order is just whatever it is on initial data. When you plug this expression back into this one final time, you get that r to the minus 4 dv r to the 5 psi naught is like the integral of u squared over r to the 7. Okay, and this integral you can compute in whatever way you want, but it gives 1 over r to the 4. Which then finally, when I multiply this thing by r to the 4 and integrate one final time in v, I just get a linear term in r because I integrate something constant. So this is how you get that final decay rate. So the actual mechanism is very simple. And you can do a similar argument for all angular modes. And it is generally related to a class of approximate conservation laws that are also related to the Newman-Penrose charges. But we can maybe talk about that after the talk if anyone is interested. Wait, where are you?
AU squared.
Yeah?
Yeah. At some point there's a regime where if you cannot take u to infinity. Why is that term? That's kind of part of it. You like the first one, AU squared minus NAR. You must have a region of u which is down there.
I don't understand. I'm integrating u squared over r to the 7. I can certainly do that.
So let's say R5 by 0.
Yeah.
Last line.
Yeah. This. Yeah.
The first term, if you let u to infinity, much bigger than r,
Yeah.
it diverges.
Yeah, sure. Of course, yeah.
Psi 0 infinity.
This is r to the 5 psi 0. So psi 0 goes like 1 over r cubed.
Yeah, but there's a moment if u is bigger than r. Like there's a regime where
There is certainly there is no regime where u is bigger than r.
Yeah, you have a color.
Well,
There's no regime. Okay,
this regime, r, u is t minus r. I'm at negative t. R just completely dominates u everywhere. Yeah.
So u
Yeah.
is smaller than r.
Yeah. 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 Yeah.
You do have an infrared.
Well, like I said, I'm not super familiar with this kind of language, but I'm working at below some early retarded time. All the way to u. So v is greater than 1, u is less than minus 1. This is this region. And so r controls everything in this region. U is t minus, u is, well, whatever, t minus r, so t is negative. Okay, so let me just quickly conclude. So these post-Newtonian methods, which you have raised doubts about them, which is, of course, perfectly fine, should be checked better, but they produce that peeling fails near scry minus. It gives us some failure of peeling. And I just assume these rates to set up some scattering problem to also prove that psi naught decays like r to the minus 4 near scry plus. And heuristics for this have also already appeared much earlier. And in fact, okay, this is what I didn't mention much, but you also have very slow decay towards spacelike infinity, which is slower than, for instance, in Krusodolu-Kleinerman. And okay, I want to emphasize again, these same results also hold for a compactly supported gravitational perturbation along scry minus. You don't need to think about this heuristic picture of infalling masses. So in particular, this means that none of the notions discussed in the beginning of this talk are capable of describing these very simple physics of the n-body problem. And at the same time, our work, because it just gives you the asymptotics everywhere to the order you desire, gives you constructive corrections to all of them. So maybe I'll just skip over this. You can also prove Bondi normalization and typical matching condition, precise decay of the News function along scry plus, and you can upgrade it all to the nonlinear theory. the corrections to Bondi coordinates if someone wants to ask after the talk. Instead of making these 1/r expansions, you get these extra terms here. And I can end now, but I could also, do I have 1 more minute? A short one. Well, so finally, I want to just mention that I told you in the theorem that this limit R to the 4 psi naught is conserved along scribe plus. This is actually a very remarkable thing because all my computations were only in the far past, but now I found a conserved quantity along scribe plus, namely this limit. And it turns out that this conserved quantity along scribe plus will completely determine what happens at late times. So the physical picture is that if I have this R to the minus 4 decay towards future infinity, then I conjecture that even for the nonlinear Einstein vacuum equations, you will get U to the minus 3 decay for R psi 4. And same for gravitational collapse. This has not much to do with what happens in the interior of space-time. It just has something to do with this thing being a conserved quantity along null infinity. And this is in stark contrast to what you have in other settings. For instance, if you have compactly supported Cauchy data, then you get U to the minus 3 minus L decay minus at least, so this is at least 2 powers faster because L is always at least 2. And okay, I won't bother showing you this picture, but yeah, this is the final conjecture, and then I'll end my talk. Thank you for your attention.